Whether you're building a new home or adding on, framing up the situation, or putting a roof over your head, if you need to rock it, roll it, or just get on with it, HOMETIME has a video to help you do it right. Transform your small bathroom into a luxurious master bath, or increase your home's value by updating your old kitchen. Keep your drains draining, your switches switching, and your footing firm. Whether you do it yourself or buy it yourself, HOMETIME's how-to video guides will help you get the results you want. Will make your next project a success. See your local home improvement retailer for the HOMETIME video that's right for you.
Robin Hartle.
And I'm Dean Johnson.
We're the hosts of the PBS TV show HOMETIME and this library of HOMETIME home improvement videotapes.
The elements of electrical work aren't difficult to understand, and this videotape will show you the steps to wire an outlet, a room, or a whole house. HOMETIME is made possible by Chevy Truck, who brings you Chevy full-size pickups, today's big pickups for professionals and do-it-yourselfers. Chevy S-Series pickups, today's compact pickups that play as hard as they work. Chevy's Astro all-wheel drive, today's mid-size van with standard four-wheel anti-lock brakes. Chevy trucks, the most dependable, longest-lasting trucks on the road. The National HOMETIME PBS series is made possible by the Stanley Works. Since 1843, Stanley's been committed to building quality tools and other products to help you do things right. Over the years, we've done many electrical jobs on HOMETIME. The best instruction for basic wiring techniques comes from this next project that I did with Joanne Liebler. Okay, Jill, this one's wire, but I'll turn it off here.
Okay.
Whether you're building an addition, refinishing a lower level, adding track lighting, or replacing a switch with a dimmer, you can save money by doing some or all of the electrical work yourself.
Once you understand the basic principles, you should be able to tackle almost any electrical project. Now, electricity is dangerous, but if you take the proper precautions and use a little common sense, there's no reason not to try your hand at it.
Remember that depending on the project you're undertaking, you might need a building permit and inspections, and these are important. Not only are they required to make your job legal, but in many cases work done without these can void your homeowner's insurance. So check with your local building department to see what's required in your area. Most of the time, if you own your own home and live in it, you can do your own wiring.
All electrical regulations in the U.S. are based on this book, the National Electrical Code. Now, don't run out and buy this book because it takes a lot of training just to learn how to read it. And we've listed some of the most frequently cited regulations in the project guide. But if you have any doubts at all about your project, you should consult with the building department or hire a licensed electrician for an hour or two to go over your plans with you.
In this tape, we're going to show you how to do a complete wiring job on a full room. In our case, a kitchen. We'll start with the rough-in, where we install boxes and run wires. Then we'll make the connections, install the devices, and install any appliances. We'll also tackle a project where we add to existing wiring.
We'll be using some specialized electrical tools, but these aren't very elaborate or expensive. They include a circuit tester, a hammer, safety glasses, a right-angle drill, lineman's pliers, a sheathing stripper, a wire stripper, needle nose pliers, a screwdriver, a fish tape, and a keyhole saw. In the course of this tape, we'll show you specific precautions you should take in working with electricity. In addition, you should follow the same common sense safety procedures you would with any home improvement project.
Work at a comfortable pace, wear the proper clothing, and follow the manufacturer's guidelines in using their tools and materials. All set?
Yep.
Okay.
There are lots of ways to describe how electricity works, but really it's not like anything else. Now, we can tell you some things that you might remember from your high school science class.
Like electricity is the flow of negatively charged subatomic particles.
Or that Ohm's law states that the potential difference times the current equals the power.
Or alternating current reciprocates in a sine wave pattern.
But don't worry, none of this will be on the final.
When it comes to the practical matter of dealing with electricity in your home, you really just have to remember 3 words.
Hot, neutral, and ground.
In 3 colors.
Black, white, green, and copper. So there are really 4 colors.
Oh, and you forgot red. But we'll get to that later on. These terms and colors are standard in all new wiring across the country. The hot wire brings the current out from the source. This wire is most often wrapped with black insulation. Once electricity has done its work, it goes back on the neutral wire, which is most often white.
The ground wire offers current another path to ground in addition to the neutral. The ground wire is always either enclosed in green insulation or is bare copper. And remember that electricity needs a complete circuit to work properly, a way out to the job, called the load, and a way back. When you work with wiring, it may not always be obvious that you're dealing with a loop. Well, for one thing, in house wiring, the 2 conductors, or 3 if you include the ground, are usually encased in a single flexible plastic sheath. This is officially known as non-metallic sheathed cable, but it's most often called Romex, which is the brand name of one manufacturer. Romex is what's used in almost all new residential construction, and it's what we'll be using in all of our demonstrations. There's a chart in the project guide which can help you identify other types of wires which you may come across.
When you flip a switch, you actually complete a loop that starts at the power source, flows through the hot conductor to the light bulb, back to the power source through the neutral conductor. Now, there are several devices designed to stop the flow of electricity between the power company and the light bulb should something go wrong. The most important of these are your home circuit breakers. A breaker is designed to turn the power off to trip should too much current try to flow through it. This protects circuits, appliances, and people. For example, if the hot lead and the neutral lead were accidentally connected, it creates a situation called a short circuit. Current will take the easiest path available to it, so it'll bypass the bulb and take the direct route back to the neutral, the short circuit. This means that current is flowing through the wires without the resistance of a load, creating a large current flow.
Well, this would be kind of like putting your car in neutral and pressing the accelerator all the way down. Without the resistance of moving the car, the engine would run a lot faster than it was designed to, and this would cause the parts to overheat and break.
A short circuit can cause the same sort of damage by overheating the wires and burning the insulation. We'll show you on this demonstration panel. If I intentionally short out the hot and neutral leads, the circuit breaker senses the extra current and turns the circuit off. Obviously, this is only a demonstration. Never intentionally short a circuit. However, there are cases where a short circuit is preferable to an even more dangerous situation. And this is where the grounding system comes in.
Well, suppose the hot lead in this toaster came loose and accidentally touched the metal case. This makes the outside of the toaster electrically hot, and there's a real risk of fatal shock for anyone who touches it.
A grounding system connects the metal frame and case of the toaster to the earth. If a hot wire touches the toaster frame, it immediately creates a short circuit and trips the breaker.
So the power is shut off before anyone can touch it. Now, on grounded appliances, all the metal frames and housings will be connected to the ground wire.
And in the wiring system itself, any metal conduit or boxes are also grounded.
Short circuits aren't the only reason for a tripped breaker. Overloaded circuits are actually an even more common cause. Well, each circuit in a house is designed to carry a maximum load, depending on the area of the house or which appliance the circuit feeds. On our demonstration service panel, the main breaker is rated at 100 amps, and there are 15, 20, 30, and 40 amp breakers for various circuits. If too many devices are running on a circuit, it draws more current than the wiring is designed for, and the breaker will trip, shutting down the circuit. If an older house has been remodeled or large appliances have been added, you may find several types of service panels. You may also find fuses instead of breakers. Cartridge fuses are used for the main and for large appliances, and screw-in usually service the general circuits.
Service panels are tricky, and they can be very dangerous, so we recommend you don't do any work inside of yours.
Instead, hire a licensed electrician to do this part of the job. Now, let's take a look at what our job will involve.
We're going to wire a demonstration kitchen for you. A kitchen has almost all the situations you'd run into anywhere in the rest of the house.
Right now, it's in what's called the rough-in stage. This is the point in construction where the heating and the plumbing and the electrical work is done. Now, if this were a real construction project, we'd have sheathing on the exterior walls and a wood subfloor would be down. but we left these off for our demonstration.
This wall will have several appliances that we have to wire for. These appliances include a refrigerator, a garbage disposal, and a dishwasher. The fridge plugs into an outlet that will mount behind it. There are 2 duplex appliance outlets above the counter on this wall. Under the sink is another duplex. The dishwasher and garbage disposal will plug into this, and the receptacle for the disposal will be controlled by a switch above the counter.
This wall is an interior wall, so it might have a heating duct like this in it. The wall also has 2 small appliance outlets above the counter and a separate 240-volt line to run the oven microwave unit. In addition to having a door, there's a cooktop along this side wall, and it gets another separate 240-volt circuit. There's an outlet here, a switch to control an overhead light, and a range hood with a light and a fan. This makes for a total of 7 circuits in our demonstration room. In a real house, the light circuit would probably go on and feed lights and outlets for other rooms. And the small appliance circuits are required by code to be 20 amps. And in a real house, they'd probably also be in the dining room, where 20 amp small appliance circuits are also code.
The electrical rough-in is done after the heating and plumbing rough-ins. This is because it's easier to run wires around pipes and ducts and vice versa.
The first step in roughing in is to install all the boxes where there will be lights, switches, outlets, or wire junctions.
There are literally hundreds of different types of electrical boxes. The most common used in residential wiring are non-metallic boxes like these. They're designed specifically for use with Romex cable. Other types of boxes, like these metal ones, are for use with various types of metal-clad cables. The chart in the project guide shows the types of boxes that may be used with different cables.
Well, how about if we get started on the back wall?
All right.
Okay. One of the most common mistakes made by do-it-yourself electricians is using a box that's too small. The NEC has very specific rules about how large a box needs to be to hold a certain number of wires. It's a complicated subject, so we've included a discussion of it in the project guide. This particular box comes with nails mounted on the side, so it's pretty easy to attach it to the side of the stud. The box also has small spacing tabs on the side. By pushing these up against the stud, I ensure that the box sticks out just far enough to get through the half-inch drywall that'll be attached later. The box goes so that the top is 46 inches above the floor. This gets it about a foot above where the countertop will be.
This box is also for an outlet above the counter, but it's going to contain more wires than the box Joanne installed, so it's a little bigger.
This larger box is a 2-gang box. It'll hold a switch for the overhead light and a receptacle. It also has cable clamps where the wires enter. Cable clamps also increase the required size of a box.
Because the sheetrock on the ceiling is a little thicker than the sheetrock on the wall, I'll need this box for the overhead light to hang down just a little further. There's a little margin for error here, so I just eyeball it 5/8 of an inch out. This box nailed into the side of the joist. This box, which is also common, has metal supports that allow you to position it in between the joist.
Once all the boxes are installed, we can drill holes through the framing for the wiring. Now this is a 1-inch bit that's attached to a 1/2-inch right-angle drill. And you'll see that it makes a hole big enough for several pieces of Romex. Okay, I'll go plug it in if you want to go to work.
All right. The holes where wire runs through the wall should go at about knee height, and they have to be centered in the middle of the stud. You can see that the right-angle drill makes it a lot easier to work between the studs. If the hole is too close to the edge of the stud, the screws that will hold the drywall in place might cut into the Romex and cause a short. So code requires that the hole be located at least 1.25 inches from the inside edge and 1.25 inches from the outside edge. In other words, right in the middle of the stud. I try to get the holes all at the exact same height. You'll see later that this will make pulling the cable easier.
Where you have to drill around obstacles, you may not be able to drill in the center of the stud. However, you're allowed to protect the wire with a steel plate. These should be available at your home center. They're required to be at least a 1/16 of an inch thick. You can see that the same sort of plates are used to protect some of the plumbing. You nail them onto the studs so no one will be able to nail or screw into the Romex.
Depending on the layout of your project, you may find yourself drilling through ceiling joists. Even on thicker lumber, try to drill in the center of the piece.
We'll run the cable around the hot air duct. We can run cable through a stud cavity that will become a cold air return for up to 6 feet. To drill your holes correctly, you really need to have a pretty good idea of where your cable will be running. We plan that ahead of time, and we'll explain each run as we put it in. Non-metallic sheathed cable, or Romex, is a do-it-yourselfer's dream come true. It makes wiring a lot more simple than running lots of individual conductors through conduit. It comes in different sizes, depending on the capacity you want for the circuit, and with 2 or 3 conductors plus a ground. The first circuit we're going to wire is the one that includes the overhead light and the switch. Now this is a single 15 amp circuit, so we'll use 14 gauge wire with 2 conductors. This is known as 14-2 Romex. For this first run, I measure out about how much Romex I need, making sure to leave lots of free cable at each end. This run goes from the service panel, over the doorway, and down to the box. I start by running the cable through the top plate, along the stud, and down in front of the panel. Code requires that Romex is securely attached to the studs. There's special staples that keep the conductors inside from getting damaged. Code also requires the staples at least every 4.5 feet. Here I put one at the top and one at the bottom of the run. Now, we thread the cable through the holes in the ceiling joists. This run through the joist is necessary because of the doorway. Where the cable is supported by studs or joists, no staples are necessary.
As soon as we get past the door, we run the cable down to the switch box. Again, we staple the cable at least twice along the side of the stud. The last staple will be no more than 8 inches from the box. You'll find this makes wiring easier, and in some cases, it's a code requirement. The cable we've just run will bring power from the service panel over to the switch. The next cable will bring power from the switch over to the light. It goes along the same stud as the first cable and gets stapled into place. It's possible to staple one cable directly on top of another. It's also possible to leave all the cables loose and staple them all into place at the same time once the wiring's done. The overhead light is one joist over from where the cable comes up, so I have to run it through one more hole. I make the bend and run it along the side of the joist out to the fixture box. This is another situation where the cable needs to be supported at least every 4.5 feet.
Right now, we've only got 2 cables running into this box, but eventually there will be 4. So in order to keep them straight, I've labeled these first 2. This cable runs out to the light, and then this hot cable brings power in from the service panel. Now, so far this has been a pretty simple circuit, but most circuits involve more than a switch and a light and 2 runs of Romex.
We also need to run power from this box to feed a range hood with a light and fan. This means another run of Romex. In a real house, you'd probably also be powering lights and additional convenience outlets in another part of the house. We run this piece down from the box. This way we can run it across to the stovetop area through the holes we've drilled at knee height, instead of working on ladders up in between the joists. We'll just leave a loose end hanging here for the hood. We'll come back and hook up the hood wiring to the Romex during the trim-out stage, after all the cabinets and appliances are in. Now it takes care of the light circuit. Code requires 2 20-amp circuits for small appliance outlets in a kitchen and dining room. Now we could run 2 lines to the 2 circuits, but to save ourselves time and money, we'll run 1 line with 3 conductors out to the room and then split it up into the 2 circuits.
I made the run from the service panel through these studs over to this box with 12-3 Romex. Now 12 means that it's 12 gauge wire, which is what's required for 20 amp circuits. And the 3 means that there are 3 separate conductors in addition to the ground. The white is the neutral, the black is 1 hot, and the red is the 2nd hot lead. The black and the red hot leads will be connected to different circuit breakers at the service panel, and the 2 circuits will share the white neutral and the ground wire. Well, you'll see what we mean more clearly once we make the final connections to the wires. We're going to use the black side to feed this receptacle, the next one down the wall, and the one near the light switch. And for this, we'll use 12-2 Romex. I run the cable down to the holes in the studs. If you've drilled your holes in a straight line, the Romex should pull through easily. A second piece runs from the second box up to the top plate, around the corner, through the joist across the top of the wall, and down to the box. This is the same box that holds the light switch, so we'll continue to label all the wires to make the final hookups less confusing.
The second set of outlets gets wired the same way, with 12-2 Romex. This run is easy because it's at knee height all the way around. Easy, until I get to this corner. One trick is to put a slight bend in the Romex and fish it through from one hole to the other.
We run 12-2 Romex from the outlet on the left side of the window to the outlet on the right side of the window.
Another run of 12-2 goes from the same outlet on the left of the window to the farthest right outlet on the wall, the outlet for the refrigerator. You'll see later why we use different cables for 2 outlets on the same circuit.
This box is for a duplex outlet underneath the sink. A dishwasher will plug into one of the outlets, and the garbage disposal will plug into the other, and a switch for the garbage disposal is located above the sink. Dishwashers, especially those with built-in heaters, draw lots of power, so we're going to run separate circuits for the dishwasher and garbage disposal.
Rather than run 2 separate cables, we'll run a 3-conductor cable carrying both circuits in on one line. And notice that we've had to drill a second set of holes for this cable. It's not unusual to find that you've got too many cables for one set of holes. Since a switch above the counter controls one of the outlets, we're running a piece of 14-2 Romex from the box below the sink to the box above the sink, which will house both the switch and one of the small appliance outlets. This is another box where we'll be smart to label all the cables to help us keep them straight.
The last 2 circuits we've run are for the oven and for the cooktop. Now these are 240-volt circuits, and they use a special type of cable. It's called SE cable, or service entrance cable. We're using heavy cable, 8 gauge. This cable has 2 hot leads and a combination neutral ground. The neutral ground conductor is a metal sheathing that's wrapped around the other 2 conductors under the plastic sheathing. In addition, this is aluminum cable. In large sizes, it's much less expensive than copper Romex. 240-volt circuits work by combining 2 120-volt circuits. And these circuits are pretty simple to hook up, since the line usually runs straight out to the appliance without any branching, boxes, or switches.
For the time being, we'll leave these ends loose. Once all the cabinets and drywall are installed, we can finish the wiring.
And that completes all of our cable runs for this demonstration area. Choosing the best path for the cables is a job that gets easier the more you do it.
Let's review where the cables are run in this kitchen. The cable for the overhead light comes over the door, down to the switch box, and then up and out to the light, and over to the range hood. 12 3-Romex feeds one countertop outlet. From there, one circuit branches back along the wall and over the door. The other feeds 3 receptacles on the wall with the window.
14 3-Romex feeds 2 circuits to a box under the sink. A piece of 14-2 runs up to the switch box next to the sink. And the 240-volt appliance circuits run to the oven and the stovetop.
At HOMETIME, we're always moving from job site to job site, hauling around a lot of tools and materials. So we need a truck that can handle the workload, like the Chevy S-Series extended cab pickup.
This truck is ideal whether we're hauling materials from this construction site or driving down the highway. Its new step-designed rear bumper and lower step-up height make loading and unloading easier than ever.
This 2-tier loading feature lets us expand our cargo space. We can store tools on the bottom and materials on the top. And with these convenient cargo tie-downs, we can make sure everything stays secure.
No matter what kind of load we carry, this double-walled construction protects the truck inside and outside and keeps it looking new.
This extended cab gives us even more space for extra tools or for bringing along a couple of helpers on the tough jobs.
This Chevy full-size pickup 4x4 is another one of our favorites for do-it-yourself jobs. This truck comes standard with a 4.3-liter V6 engine to give us enough torque and towing capacity to clear a couple of trees from this new home site. Okay, back up a couple of more feet.
Also standard are its rear-wheel anti-lock brakes that give you controlled, smooth stopping. That's the kind of security you should demand from any braking system. Chevy's got it.
Even with all the work we put this truck through, it still looks like new. The double-walled cargo box keeps any wear on the inside from showing through on the outside.
And all of Chevy's fleet-side pickup trucks give us the option of 2-tier loading. So we have the option of using the box as is or creating a second loading level. Okay, that's good. Whether we're carrying passengers, hauling cargo, or pulling a trailer, this all-wheel drive Chevy Astro passenger van is the perfect vehicle.
With its combination of all-wheel drive and 4-wheel anti-lock brakes, this van gives us the control we need, even in the worst weather.
In fact, the Chevy Astro van has the largest towing capacity of any van in its class, and its versatility makes sense for every do-it-yourselfer.
The spacious cargo area is ideal for hauling these shrubs or any other material. And with these available Dutch doors, loading is even more convenient. No matter what size of your project, you'll get the job done with a Chevy truck.
They've been a big part of every HOMETIME project, and it's easy for us to see why the most dependable, longest-lasting trucks are Chevy trucks.
Now that we've run the cable, we're ready to make the connections between the cables inside the boxes. Take a moment at this point to check all of your cable runs and make sure they turned out as you expected, and that all your boxes are the right sizes.
Even professional electricians will find themselves enlarging a box at this stage. Now we want to cut the wires to their final length. Code requires that each wire extends 6 inches from the front of the box. This is called 6 inches of free conductor. I hold the cable next to the box and cut it to the right length. You'll find that these lineman's pliers are a useful tool in wiring. Next, I strip off the outer plastic sheathing. This little tool has a tiny tooth on the inside. I slide it up over the cable, squeeze it gently, and pull it down past the end of the cable. This splits open the sheathing. Now I peel it back and cut it off. To get the wires into the box, we have to break through small plastic holes on the top called knockout tabs. You punch through the tab with a screwdriver or handle of the pliers. Now I push the wires into the box. This box also has a metal cable clamp that will hold the wires in place. I fish the conductors past these. You can see now that I cut the sheathing of the Romex so that it reaches just past the clamp. I'll cut and strip all cables that run into this box. But here's a tip. We leave one cable about 8 inches longer than we need. This will make it easy to make a pigtail, and we'll explain what this is in a minute. The cable clamps in this branded box are small metal flanges. Other brands may have plastic flanges or metal collars that screw down. Now it's time to make connections between the conductors. I'll trim the rest of the cables.
Okay, I'll finish this up. In this box, the first thing we can do is connect all the ground wires together. There's only one ground system for the whole house, so we can connect all the ground wires for every cable that comes into this box, regardless of which circuit it's for. To start, I'll trim off the pigtails. A pigtail is just a short piece of wire to make a connection from a group of wires to a device, in this case, the switch. By cutting off these conductors, we'll have a hot, a neutral, and a ground pigtail if we need them. Then I group the ground wires together, dressing the hots and the neutrals out of the way. Once I've twisted the wires by hand a little, I can trim the ends to the same length. Then I grab the end of the group and the lineman's pliers and start twisting. The ground wires can get wound all the way to the back of the box. Twisted connections with electrical wire should always be twisted together in a clockwise direction. Once the bundle is twisted together, the ground pigtail is wrapped in. It takes a few more twists of the group to make this connection. Then a wire nut secures the group. The wire nut also screws down in a clockwise direction. I gently fold the ground wires into the back of the box. Folding wires into a box is a bit of an art, and that's one of the reasons why box sizes are so important. Make sure you use the right wire nut for the number and size of wires that you'll be connecting. The packet will tell you what sizes the wire nuts will work for. Before we make the rest of the connections, we'll strip the ends. We need to expose about 1 inch of bare copper on the end of each wire. The tool for this job is a wire stripper. I fit the number 14 wire into the notch, squeeze the handle, and pull the insulation off. I'm only going to strip the wires for the lighting circuit now. Actually, it's a better idea not to strip any wires until the trim-out stage. We're stripping these to make a point about how to make connections. The next connection I make will be between all the white neutral wires for the lighting circuit. I hold the ends of the 3 white wires together and grip them with the pliers. Then I turn the pliers until the ends of the wires are twisted tightly together. Although grounds from different circuits can be attached together, the neutrals can't. So I leave the 12-gauge neutral for the outlet circuit separate. I secure these with a wire nut, this time using a slightly smaller size nut than the one I used on the ground wires. Wire nuts not only help keep the wires together mechanically, but also ensure that they stay in contact electrically. Then I fold these wires back into the box and out of the way. Now all that's left is to hook up our hot leads, and this is where our labeling pays off. This is the hot lead that brings power into the box. We want to attach it directly to the wire that feeds the range hood, but we want to use the switch to separate this hot lead from the black wire that feeds the light. To make the connection to the switch, I'll use the extra bit of black wire for a pigtail. Again, I twist the ends of the wires together and screw a wire nut down onto them. There. The connections for this box are finished. All that's left is to attach the devices. Normally we'd wait until the drywall and cabinets were in before we'd do this. Then we'd come back and install the switch, the outlet, and the cover plate.
But for our demonstration, we'll install these now to show you why we made the connections the way they were made. And we'll start with the switch. The two screws on the switch are brass colored. This helps you figure out what wire is attached to it. A switch always interrupts the hot side of a circuit, and black wires usually get attached to it. A brass colored screw is a standard indication for a hot lead. To attach fixtures, I use needle nose pliers to put a small hook in the end of the wire. This hook fits around the screw, and I tighten the screw down. It's important that the hook in the wire is clockwise, so that as I tighten the screw, the action of the screw tends to pull the wire into the connection. It doesn't really matter which wire goes to which screw, as long as the hot black pigtail connects to one, and the black lead that goes out to the light connects to the other.
We'll also get a little ahead of ourselves for demonstration purposes and install this simple ceiling light. The color coding of the wires makes this pretty simple. On this fixture, the ground wire connects to a green screw on the fixture strap. The two neutral wires are already connected, so now I connect the two hot conductors with a wire nut. Then I attach the fixture to the mounting strap in the ceiling box. The mounting screws connect the base of the light to the ground system.
So this lighting circuit is wired and ready for power. Now let's try to picture how the current would flow through these simple connections in this box. If the power were on, the current would already be flowing to the range hood. It comes into the box in the black wire from the service panel and goes out to the hood. Assuming the hood light is on, the current then comes back into the box on the white neutral lead and then back to the service panel, a complete circuit. The current is also ready to flow to the light, but it only gets as far as a switch, which is off, stopping the current. When the switch is turned on, the current flows through the switch and out to the light. Then it comes back on the white lead, joins up with the rest of the neutral circuit, and flows back to the panel. We'll also wire up this outlet here. Now there's only one 12-gauge cable coming into the box, so we know that it feeds the receptacle even if we hadn't written it on the Romex. The receptacle has a pair of brass screws, a pair of silver screws, and one green screw. The brass screws are for the hot lead, the same color coding as the screws on the switch. The silver screws are for the neutral, and the green screw is for the ground. This color coding is pretty standard, and it's important to honor it. The ground wire is the first we hook up. The copper pigtail that we installed when we connected all the ground wires together gets a hook in the end of it, and then gets attached to the green screw. For the other two leads, we're going to use the quick connect feature of this receptacle. In addition to the screws for the leads, there are small holes in the back of the outlet. I can push the end of the lead into this hole, where a small metal flap makes the electrical connection and holds the wire in place. If you ever need to remove a quick connect wire, slip a thin screwdriver down the slot next to the hole. This releases the wire. There are quick connects for the hot and the neutral, but not the ground. This requires a screw connection. This is the last receptacle on our circuit. We still have to wire the other outlets leading up to it.
Receptacles where power comes in on one cable and then travels out to different parts of the circuit on another cable get wired with pigtails. And this is probably the most common box configuration you'll find in a house. For this receptacle, the power comes in on this cable and goes out to the receptacle Dean just connected on this cable. I've connected each pair of hot, neutral, and ground wires together, and I've run an appropriate pigtail out from each connection. The pigtails will attach to the receptacle. Well, I'll get started on the GFI.
All right, good. Remember the 12-3 Romex brings two circuits to this box. They'll get connected to the two legs of 12-2 Romex, which includes the boxes we've been working on. I've already connected all the ground wires together, including a pigtail to connect to the outlet. I fold the grounds into the back of the box. Now I can do the neutrals. The stripped ends get twisted together and secured with the appropriate size wire nut. This connection is where the one neutral conductor from the panel splits into two neutrals, one to feed each circuit. And I've included a white pigtail for the outlet here. Now I've got two incoming hot leads left, one black and one red. I connect the incoming black hot to a pigtail for the outlet in this box, and to the black lead that feeds the receptacles on one circuit. To wire the second circuit of receptacles, all I have to do is connect the incoming red hot lead to the black wire that goes out to feed the second circuit. The ground and the neutral for both circuits are already connected.
This box is the first outlet for the second of our two small appliance circuits, and it's right near the kitchen sink, so code requires that we install a GFI receptacle. GFI stands for Ground Fault Interrupt. A A GFI receptacle constantly monitors how much current is going out to a device on the hot lead and how much is coming back on the neutral. Normally, these two amounts of current are the same. In a fault situation, the dangerous current is the current that doesn't come back on the neutral. This current might be trying to return to ground through other routes, possibly through a person who's in contact with water. A GFI senses differences in current as small as 5/1000ths of an amp and shuts off the power within a 40th of a second. GFIs are required by code in basements, bathrooms, garages, outdoors, and within 6 feet of most sinks. They're wired a little bit differently than regular outlets. Well, for one thing, they've got 2 extra screws. These hot and neutral screws are labeled line. This is where the incoming power is attached. Then these extra screws, labeled load, feed power out to the other outlets. Any outlets attached to the load side will also receive GFI protection from this device. So we'll wire this receptacle to the right side of the sink to the first GFI and get GFI protection without having to use a second GFI device. However, this outlet is for the refrigerator, and it doesn't have to be a GFI outlet. And it's probably a good idea if it isn't. That's because power surges from the motor could cause the GFI to unnecessarily trip itself. And that might cause your refrigerator to turn off and spoil all your food. So we've run 2 12-2 Romex cables from this first box. The first one will feed this receptacle, which is the GFI outlet, and the second one will feed the refrigerator. Back in the first box, all the grounds are attached together normally, with a pigtail to the outlet. The incoming neutral attaches to the neutral for the refrigerator and to a pigtail for the outlet here. The incoming hot gets attached to the black hot for the fridge and to a black pigtail for the GFI. The hot and neutral for the second GFI outlet will be attached to the load side of the GFI receptacle. If we were to install the GFI now, here's what it'd look like. Current comes in and flows directly to the refrigerator through one 12-2 Romex. Current also feeds directly to the GFI outlet through the pigtails and then goes on to the second GFI outlet through the second 12-2 Romex. There's one more cable in this box we haven't accounted for. That's the cable for the switch that controls the garbage disposal, which plugs into a receptacle under the sink.
And that box has a few interesting twists to the wiring. First of all, there are 2 circuits being fed by a 14-3 Romex cable. That accounts for the red wire. The ground wires are already connected. The only other connection I need to make now is to connect one of the hot leads, in this case the red one, with the white lead going to the switch. It's a special case to connect a hot wire with a white wire, but it's appropriate here because we're creating a switch loop. A switch loop sends the incoming current from the hot lead out to the switch and back again before it's connected to any device, like a light or an outlet. Let's install this outlet to see how it all works. Before I make any connections, I have to separate electrically the top and bottom outlets on this receptacle. This is done by breaking the small metal tab between the screws on the hot side of the receptacle. Once this piece is removed, each outlet will require its own hot conductor. Now I connect the ground and the neutral conductors to the receptacle. I'm left with terminals for 2 hot wires. I connect the black hot lead coming back from the switch loop to the terminal for one receptacle. This way, half of the outlet will be controlled by the switch. The second black wire brings power straight from the panel, and I'll connect it to the terminal for the other receptacle. This means that it will always be on, and we'll plug the dishwasher into this. When you create a switch loop, it's important that you send the current out on the white lead to the switch so that it comes back on the black lead. This way, the hot lead will be a black wire where it makes its final connection to the device. There are a few other configurations for switch loops. Check the project guide for illustrations of some others.
Well, we're done with the rough-in. Now remember that normally at this stage we wouldn't have put in any lights or switches or outlets. And the few that we did install are for demonstration purposes only. And now we'll just have to take them out.
With the rough-in complete, we neatly tuck all the wires back into the box. If this were a real construction situation, the next electrical work wouldn't happen until all the drywall, cabinets, and plumbing fixtures had been installed.
And of course we'd need to get a rough-in inspection before the drywall goes in. That way we could make any corrections now instead of ripping off drywall later to make them.
Our demonstration shows the basics of roughing in 7 circuits. In a complete house, there might be up to 30 circuits, so the scope would be entirely different. In fact, let's take a look.
If a house has a basement, you'll often find that most of the cable runs are made here. Groups of several cables can be run to various points under the first and second floor, where it's easy to run them up to wherever they're needed. The trim out is the last step in a new electrical installation. You can see that all of our finish work is done. Now we can finally hook up all the switches, receptacles, light fixtures, and appliances. We've mounted the boxes properly because they're flush with the surface of the drywall, or a little behind it. Code allows the boxes to be recessed up to 1/4 inch back from the drywall. This part of the job is pretty simple. Just consult your plan and hook up the appropriate device to each box and put on the cover plate. The color coding on the screws makes this pretty easy. If it isn't clear on the fixture you're dealing with, well, then there are other indications. The ground screw connects to the mounting strap. It's a hexagonal screw and it's often labeled with the letters GR. The hot side of an outlet is always on the side with the shorter slot on the face, and the neutral side always has the longer slot on the face. Each outlet box should have 3 free wires. These get attached straight to the appropriate terminals on the device. Although there are 2 hot and 2 neutral screws on the side of the outlet, we only use one of each. Some people use both screws to avoid making a pigtail. We don't recommend this.
The only exception would be on our outlet under the sink, where each hot screw feeds half of the outlet. There's only a little bit of detective work left when you have to trim out a double box, like this one that has both a light switch and an outlet. I have to look at the groups of wires and figure out the left group is for the receptacle, since it contains a hot, neutral, and ground from one piece of Romex. The remaining 2 black leads are for the light switch. The 2 switch leads can go on either switch terminal, and make sure you install the switch so that it's off when it's flipped down.
The switch for the disposal is a case where we connect a white lead to a switch terminal. Remember that it's not a neutral. It's part of a switch loop up from the outlet below the sink. For this GFI outlet, the pigtails connect to the line side. The 12-gauge wire feeds the other 20-amp GFI protected outlet. When you screw a fixture down, the metal straps at the top and bottom should rest on the drywall. Don't screw them down any farther. There, that's good.
Making the connections that feed the cooktop and the oven are a little different. For one, the wires into these appliances run through armored cable coming out of the back of the units.
Because of this, we have to use metal boxes to make the connections between this cable and the SE cable that comes from the service panel.
The SE cable has been run into the cabinet next to where the oven microwave unit will go. First, I slide a cable clamp up the cable and tighten it. Now is also a good time to strip off the sheathing. Next, I mount the box to the back wall of the cabinet. It helps that the SE cable has been run out of the wall right next to a stud. This way I can screw the box securely into the stud. Unlike the boxes we mounted in the walls, this is called a surface-mounted box. I secure the SE cable to the box by tightening down the lock nut for the cable clamp.
Okay, go ahead with your hand there.
Okay. How you doing?
Through?
One last push ought to do it. There.
Okay, I'll pull the cable through.
The armored cable from the appliance comes into this cabinet through a hole that's been drilled between the 2 cabinets. This cable is then run into the junction box and clamped. Notice that the clamp that holds the cable looks a little different than the clamps for Romex and SE cable. Each type of cable has a specific type of box and clamping hardware. Once both cables are secured, I'll be ready to make the connections. Joining aluminum wires like SE cable requires an extra step. Aluminum oxidizes over time, and this can weaken the connection and cause it to heat up. So we'll be coating all of our connections with an anti-oxidizing gel. Remember that with 240-volt circuits, the ground and neutral are combined in one conductor. So make sure that the SE cable ground is connected to the white or copper lead coming from the appliance. This oven has both a white neutral and a copper ground. Some local codes may require them separate for certain situations. Now I apply the anti-oxidizing gel. I cover the connection before I twist on the wire nut. The two hot leads are joined to the hot leads from the appliance. One thing that makes 240-volt circuits simple is that it doesn't matter which hot supply lead goes to which appliance hot lead. Each of these connections is also covered with gel before the wire nut goes on. The last step is to put a cover over the box. Covers are required on every box in a house. Since this junction box doesn't have a device, like a switch or an outlet, we use a solid cover. Appliance junction boxes are sometimes installed on the wall directly behind the appliance. In this case, they have to be in a place where there's a recess in the back of the unit. The advantage to the way we've done it is we're still able to access the box without having to pull out the appliance. We'll install the junction box for the cooktop the same way. This time we'll install it in the cabinet underneath the cooktop.
We're also ready to connect the range hood, and I've already mounted it under the cabinet. The electrical connections are pretty easy to make. The cables are run into the unit as it's mounted. Once inside, there are just the 3 basic conductors coming in. The incoming ground goes around a green ground screw. The white goes with the white, the black with the black. A cover holds all the wires in place under the hood. And the wiring for the kitchen is done.
All we have left is the wiring at the service panel.
Tying into the main service panel can be a bit intimidating. We recommend that you have a licensed electrician handle this part of the project. While you're at it, have the electrician look over the rest of your project too.
The electrician will begin by connecting the incoming leads. 2 hot supply leads run to the main circuit breakers, which are attached to 2 connection bars called buses. Breakers for the branch circuits draw current from these. All of the neutrals and grounds connect to a neutral bus bar. To wire the panel, we run the supply and branch cables inside the panel and strip them. The branch circuit breakers snap in, making contact with one of the 2 hot bus bars.
A copper ground wire runs out to a stake in the ground or to the house's cold water pipes, depending on local codes. This ground wire is connected to the neutral bus bar. And since this is a service entrance panel, the metal case of the panel is connected to the neutral bar with a short strap. The incoming neutral conductor also connects to the neutral bus, usually with a special lug.
And the 2 incoming hot leads connect to the main breakers. All of the neutrals and grounds from the branch circuits connect to the neutral bus bar. This only happens in a main panel. A sub-panel will be wired differently. The individual hot leads are connected to the individual breakers. Now remember, this is just an overview of how a service panel is installed. Don't try this yourself. Hire an electrician.
Now there's one important distinction between a main panel and a sub-panel we feel you should be aware of. In a sub-panel, there's a separate grounding bar. The ground wire from the main panel attaches here, not to the neutral bus bar. There's a separate neutral lead from the main panel that attaches to the neutral bus. And the two hot leads connect to the two hot bus bars. The branch neutrals go to the neutral bus. The branch grounds go to the ground bar. And the branch hots go to the individual breakers. Now, back to our main panel. All of our breakers are still turned off. The panel is powered, but the circuits aren't. We'll turn on each individual circuit one at a time in order to test them. We start with the main breaker. This powers each individual breaker, and we'll turn these on one at a time, starting with the range hood. How's it look?
Looks good here, Joe.
Good.
Now turn on the first small appliance circuit. It's a good idea to test each circuit the first time you turn it on. One way to do this is with a simple voltage tester. This is usually just a small light with two leads. I insert it into the two slots of the outlet. Since the light goes on, there's current. This type of tester glows much brighter when connected to 240-volt circuits. You can also make some elementary tests of the ground system with this tester. If the tester glows when it's connected between the hot slot and the ground slot, you know that the ground circuit is providing the proper path to earth. It should also glow when testing between the hot and the cover plate screw. Okay, I'll check the rest.
Okay. You can perform some slightly more sophisticated tests of your circuits with this type of tester. Two amber lights mean the circuit is wired properly. Different combinations of amber and red lights indicate different problems, like no ground or reverse polarity, which is having the hot and neutral backwards. You may want to have both types of testers around, especially if you're planning a remodeling project. Ooh, like putting in a recessed light in the soffit over the sink.
All right, well, let's get started.
Okay.
There are no hard and fast rules to changing or adding lights, switches, or outlets. You have to use common sense and some of the basic electrical knowledge that you gained from our new installation project.
In an add-on situation, you can create a new circuit or draw power from an existing circuit. We're going to tap into our lighting circuit, but you need to be careful about this. If you add too many devices into an existing circuit, you could end up with a circuit breaker that's constantly tripping.
And you can't tap into just any old circuit. These small appliance outlets aren't supposed to power any lights, so we'll have to tap into the lighting circuit.
The most important part of a job like this is to make sure that you're not working around live wires. I turned off the breakers for these two circuits, and I put a note on the panel so no one will turn them on while we're working on them. I tested the circuits before I took off the cover plate. Now I'll test them again. I test the hot and neutral terminals on the outlet and the hot and the ground. For a switch, I test between both the screws on the switch and the neutral and the ground. I want to make sure there's no power at all in the box. Now I pull as much as I can out of the box. I'm going to need some room to work. I need to get cable into the box, so I'll have to punch out an additional knockout tab.
We've also drilled an additional hole in the top plate. Now we want to run a cable up from the box, through the stud cavity, and up through the hole in the top plate. Normally there'd be drywall on a wall like this, but we've installed a sheet of plastic to show you how we'll make this run. And to accomplish this, we'll be using this tool, a fish tape. I insert it in the hole in the box and aim it up. It's going to be a hit or miss operation. It'll probably take a few attempts before I get the end of the fish tape to poke through the hole in the top plate. It helps if one person works the tape and one person waits for it on top.
Okay, got it.
Once the fish tape is through, we hook the end of some 14-2 Romex to it and pull the cable down into the box. Okay, I got it, Joe.
We could have run power for our new light a couple of different ways. We could have run a new cable from the service panel. We could have installed a junction box and run a cable from it. Or we could have chopped out some of the drywall to make the threading of the cable a little easier. Now, we'll just run the cable across the ceiling to the other side of the room. Most rooms will have either an attic above them or a basement below. These are usually the best and easiest ways to run cable horizontally. In an attic, you may have to pull aside some insulation to find and run the cables, and be careful to walk only on the joists.
We'll need some new holes at the top of the wall for cables. In addition to holes through some joists, there has to be a hole down into the stud cavity where we'll put the switch.
The recessed light that we're installing needs a hole in the soffit for mounting. And I used the light itself as a guide to mark the hole. Now we'll just cut it out with a keyhole saw. We're installing a new switch box also. This requires another hole in the wall.
For this light, we'll run incoming power to the light fixture. Then we'll run cable for a switch loop through the ceiling joist here down to the switch.
Okay, I'm ready when you are.
The run down this stud cavity is a lot easier since we've got a larger opening to aim for. We can just reach into the stud cavity and feel around for the cable.
We're going to use a special type of box for this switch. It doesn't have to be attached to a stud. In fact, the drywall holds it in place, so it's perfect for add-on situations like this. The metal flaps on the side spring out as I push it into the wall. Then I tighten down the center screw in the back. This secures the box against the drywall.
Because we've created a switch loop, the connections in the light are similar to the connections we made in the switched outlet for the disposal. All the grounds and all the neutrals are connected together. However, the incoming hot is connected to the white wire going to the switch. Then the black wire returning from the switch connects to the black lead for the light. To mount this light, I slip it up into the opening. Then these small clips secure it by digging into the drywall. Installing the reflector and bulb finishes the work here.
This switch is wired like any other, so the two leads attach to the two screws. However, we do have a ground wire with nothing to attach it to. Usually this just folds up in the back of the box.
Now it's time to finish tapping in. We'll connect our new cable to the cable running power for the lighting circuit into the box. Then I remount the devices and put on the cover plate.
Okay, Dean, I'm turning it on.
Okay, this works here.
Good. The switches we've installed so far are simple two-way switches. But a common feature of most homes is a set of 3- or 4-way switches. These allow you to run a device, usually a light, from 2 or more locations. And the theory behind them is pretty clever. These switches operate by directing the current down one of 2 possible paths. These 2 paths are made up of wires called travelers. In this configuration, current comes into the first switch on the hot lead and goes to the second switch on the top traveler. Throwing either switch stops the flow of the current and turns off the light. But even if the current has been stopped by throwing the first switch, the second switch can still turn the light back on by completing the circuit on the bottom traveler. So 2 3-way switches can control the same light. Adding another type of switch, a 4-way switch, allows even more switches to control one light. A 4-way switch simply reverses the connections between the 2 travelers. And there can be as many 4-way switches between the 2 3-ways as you want. Let's wire a few on this demonstration to show you. The circuit has a continuous ground and a continuous neutral, and these have been connected inside each of the boxes already. The first switch is a 3-way switch. The incoming hot lead is connected to what's called the common terminal. The common terminal is usually a darker screw, or, as on this switch, a copper screw. The 2 travelers to the next box are connected to the 2 other screws. The ground, neutral, and 2 travelers are carried to the next switch through a piece of 14-3 Romex. The 2 hot leads in this cable, the red and the black, are the travelers. The second box gets a 4-way switch. The toughest part of wiring a 4-way switch is determining how the screws are paired. Here, you see we have 2 copper screws and 2 brass screws. Most often, one pair of travelers is connected to the screws at the top of the switch, and the other pair, which leads to the next switch, connects to the screws on the bottom. In the third box of this demonstration, the hot that goes out to the light is connected to the common terminal. The incoming travelers connect to the two other screws. When you're working with travelers, it doesn't matter which one of the pair attaches to which of the two traveler screws. The common screw is the only one that has to be connected to a specific wire.
Okay, Joe, this circuit's hot.
Okay, think we're ready for a test.
Works.
Good.
3- and 4-way switches may not always be wired so that the power travels through all the switches to get to the light. So once you're familiar with the concepts involved in this configuration, check the project guide where we show you a few other possible configurations.
We've tried to show you as many wiring configurations as we can, but every wiring job is going to be different. We hope you'll be able to take the techniques and principles that we've demonstrated and apply them to your own wiring situations.
Whatever job you do, make sure you thoroughly research local codes. Most inspectors are happy to answer questions, and always work with a permit. If you don't, not only is it illegal and dangerous, but it could also void your homeowner's insurance.
And scout around for an electrician who's willing to work with you. Well, someone who will do the work inside the service panel and check out the rest of your project. And remember, watching one videotape isn't going to make you an overnight expert. Don't be afraid to do more research and ask questions.
So good luck with all your home improvement projects. I'm Dean Johnson.
And I'm Joanne Liebler. Thanks for watching.
Home Time is made possible by Chevy Truck. Who brings you? Chevy full-size pickups. Today's big pickups for professionals and do-it-yourselfers. Chevy S-Series pickups. Today's compact pickups that play as hard as they work. Chevy's Astro all-wheel drive. Today's mid-size van with standard 4-wheel anti-lock brakes. Chevy trucks, the most dependable, longest-lasting trucks on the road. The National HOMETIME PBS series is made possible by the Stanley Works. Since 1843, Stanley's been committed to building quality tools and other products to help you do things right.